Okay, very welcome from my side. My name is M.Binder and I am coming from Fraunhofer IGCRE, and my talk is about automated sensor integration and printing using laser-based powder bed fusion of metals. And I'm trying to switch the slide and it works. And yeah, just shortly about us, because there's so many Fraunhofer institutes in Germany. We are located right next to Munich in Augsburg mainly. So we have like 3 departments, one composite department, one processing department where I belong to and our entire additive manufacturing facilities belong to, and another one in Garching, which is about casting, and they also do additive manufacturing and indirect additive manufacturing of sands using binder jetting. So also a small part there. And I'm trying again. Yes. Thank you so much. And just another slide about our lab. So we have a joint laboratory which is called the AAM lab, together with the Technical University of Munich, the EWE. And together we have a lot of different machines from sand side to metal to polymer. And today we are talking about the metals. So we have different machines that we use for our studies in the field of multi-material and sensor integration. And this is an Equality 1 SLM Solutions 280 and SLM Solutions 250, which are made for sensor integration and multi-material processing, where you're also able to print sensors. So just want to introduce our work, why we are doing what we are doing. So we have a big focus on laser-based powder bed fusion because it's the most widely used AM process in industry. I think that's known. And we see a lot of different advantages using additive manufacturing for sensor integration. So we can manufacture sensor adapted housings, let's say, during the process. We can capsulate the sensor entirely, so we can insert a sensor during the process, which is like capsulated entirely and protected from the environment. And the layered buildup makes it possible that we can insert a sensor at any time during the process in our part. So there are no limits anymore. And also industry and other research forecasts just see extensive future in developments and potentials in the next years. But enough about like the motivation. So what am I talking today about? So it's like about sensor integration, which means we have an existing sensor which is like inserted in our part during the process. This can be done manually, but also automated just by using a robot inside your chamber. And there's a second approach, just the additive manufacturing of the sensor itself, but you need like multi-material processes for this. And therefore, this is like a different approach. And if we take a look from the left to the right, I would say you can do this right now in your machine. If you have one at your laboratory for the automation, it's like the next level because you need an automation unit. And the best approach, because it's like it's like a full process integration, is if you can just manufacture the sensor during the process. So this has the highest process integration, but as you can also see, if you take a look at maturity here is low because there are like low amount of machines which are able to process multi-material. But there was a lot of more work done in the field of manual sensor integration and also recently automated sensor integration. So my talk is about all 3 of them, and I will give you just an overview what can be done in these fields. So when I talk about like manual sensor integration, how does this work? So we just built something up by laser-based powder bed fusion and have like process dependent our part, and inside there's powder. Afterwards, like during a process interaction, we can remove powder out of the cavity and insert any part, could be a sensor in our case, inside the part, and then we proceed with the process. So this is like a very simple scheme. You can imagine that there are more challenges if you want to do this, but that's like the basis. if we take a look into how we can realize that, you see demonstrated part here. It's an accelerated pedal, which looks like that. It's around 150 millimeters from left to right here in this position, and which is meant to be to put like force on the pedal side. And then we have integrated sensors which measure the force. And how did we do this? You can take a look here on the left side on the manufacturing part. We build up our part, and then you see section A in this case. And you see part of the section A here. And we've also printed electrical conductors during the process. And what did we do here? We have a monomaterial process that used the same material, which was aluminum alloy, LSA 10mg, for the manufacturing of the conductors. Then we inserted a sensor, and we just inserted a PT100 sensor, which is temperature sensor, and also a weldable strain gauge, and connected them to the conductors. And then proceeded with the process. What comes out, you see here after post-processing. And then, maybe I give you just another hint why we used the PT100 temperature sensor. It's just because of the environment. You can imagine you have this part in the cold temperature and the hot temperature, and you can just use this temperature knowledge to define the force that is applied on the system, and can use this just to calculate the real force of a user. And we've done also tests, and you can see that an applied force of 200 Newton results in a similar weldable strain gauge strain. So you can use this part with integrated sensors as it just was meant to be. Second, I want to talk about like automated sensor integration. There's like almost no difference beside the case that the process interruption, which is bad for the process, as we all know, is shorter. You don't have to open the process chamber, and it's automated. You don't have to wait until like any user comes in on the weekend, for example, to insert a sensor. It can be just be fully automated. And we've also done this, and it doesn't work. I'm sorry. In our Economy 1 machine, so we've developed an automation unit which is mounted on the recoating unit. So you just saw the recoater, which is like recoating powder over and over again, and we manufacture here in that area. And you've just seen like a cavity that we've manufactured, and it's just like a small magazine with RFID tags, and we can insert these RFID tags during the process by vacuuming the cavity and picking and placing RFID tags into these cavities during the process. And this is fully automated, so you can just start the process, and this will take place whenever it's necessary. And this is like a more prototype status. We have already got like a second version of this, which is capable of inserting sensors during the process. And in this case, we've manufactured RFID rings just because we wanted to manufacture something which is understandable, easy understandable. So you can save information on the inside of this RFID tag, and it's a low frequency RFID tag which is capable to send through metal. And you can see here on the right side the reader distance in the beginning before integration, which was around 12.1 millimeters, and afterwards around 8 millimeters. So you can still use it for opening doors, or for example in the future paying with your credit card if you put the information on it. So just to give some use cases. And then on the next slide, I also want to show you another part that we've manufactured with automated integration. So we've combined again the manufacturing of the electrical conductors. So we build up conductors as you've seen at the moment before. So we just use the same material, in this case 316L, to build up conductor which goes like in the part, from the outside in the part. And then we have our interruption plane and insert on PT100 sensor here and just finish the part. And I think I've missed to say that, but it's kind of important. You build it up, and insert the sensor, finish the part, and then you can imagine that your electrical conductor is like in the middle of your part and not hold it anyhow. So after the process, we fill in, or we remove the powder and fill in an insulator, which is just like isolating the electrical parts from another, and then you cut the part, and as soon as you cut the part, these different wires become like isolated from the rest of the part. So this makes this feasible. Sorry for missing this in the beginning. And I've just shown you we've manufactured these parts, and then we insert the PT100 also via automated sensor integration. And the electrical wires of the PT100 are just placed on top of the additive manufactured wires, and then you get a joining zone via laser. So we just use the laser beam to connect these both. This works. We have a joining zone, and we are also able to just show that it works by using it. So in this case, we put it into hot water, 100 degrees hot, and measure the time, how long it takes the entire system to reach that heat. And it takes some time because of, it was at room temperature, so it just needs some time to adapt because it has a specific mass, and this needs to be warmed up. But in general, it works. So that was it to the integration of sensors. And now I just want to give you another input regarding multi-material manufacturing, in this case of sensors. So we have a multi-material process in our systems, in our quantity 1, SLM250 and SLM280, and we have made these adaptations on our own. So it's like an own development. And we use like recoaters, which have the powder on the inside of the recoating system, and manufacture multi-material as I show you now. So we just place one layer of one material, solidify that layer. So we have steel, for example, and the other one, the orange one, is copper. And we have, in addition, vacuuming unit on the recoating unit. So it's just able to vacuum one layer and a little bit more. That's really precisely feasible, which is like, hard to believe, but it is. And then we have like room for a second material. So we can insert a second material and solidify that second material. So we have like the possibility to have any material at any position in the entire part. And that's possible. We've done this with 3 different machines. The SLM280 is the best machine right now. So we've just printed such a big part, which is like using copper and steel wherever you want it. I didn't bring it today, unfortunately, but you can look it up if you want on our website. And then you jump to the next layer. I've forgotten to say. And how does this look in the machine? So you have one layer of steel that you just solidify. And then, again, the other material, it takes a little bit of time. So just say you have like in the end multi-material batch of powder, which is also kind of a problem, but we have also solved that. So we have like magnetic separation and separation by sieving. So you can separate all different materials you want to by these both principles. So on the one hand, by using one magnetic and one not magnetic system, or by using different particle size distributions that you can sieve in between. Okay. To make it even more complex, we are also able to print 3 materials at the same time by the same approach, and you can also think of 4 or even more if it really matters. And print it, for example, a component with tool steel on the outside, then an insulating material, in this case ceramic, and a conductor made out of copper in the middle. But you can hardly see it because it's like different gray areas, but it worked. But it's like it's a process which has an early TRL, so it's like pretty hard to print 3 materials at the same time, especially with ceramic. And this is different to the conventional multi-material process, which runs pretty good so far. And big introduction, finally coming to printing of sensors. So we used that approach to print sensors, and in this case, just these both conductor pads that we bring together. And one side is made out of alumel, the other side is made out of chromo, and together they form a thermocouple. So we can just print a thermocouple using this multi-material approach. And what you can see here is like a fit of a conventional thermocouple and the additive manufactured thermocouple, and this is, let's say, kind of easy to do. So if as soon as you're able to print these both materials together, it wasn't a big deal to make them fitting into the same graph. So it works from 50 degrees to 350 degrees exactly like a conventional thermocouple. Second, what we also do is printing strain gauges that we've inserted in the acceleration pedal the moment before. We are also able to print it. Here you see some pre-studies that we've made. And just looking on the clock. Some pre-studies that we've made that you can insert into a part. So you can print any part and print a strain gauge in it. And we've just printed these parts and evaluated the performance of these strain gauges, and that it works. You can also see in that curve. So we have our reference strain gauge in blue, which is like really clear and in its behavior. Then we have our additive manufactured one, and you see it's like doing almost the same, but maybe not as precise as the other one. So it works in principle, but we have to put much more effort into this to get a better precision of that system. So that's like almost the end of my talk. So I summarize and give a short outlook. So what have we done so far? We have done manual sensor integration, automated sensor integration, and also the printing of sensors and conductor paths. And the next steps are that we are like trying to industrialize the process. We want to increase the TRL, that the applications become more and more, because there are not so many multi-material applications so far in the field of metals, because it's still not feasible. So that's like our next approach to improve, for example, parts by simulation and then print it afterwards to show the better performance of the parts. And we want to overcome challenges in the field of metal ceramic combinations, because the machines that we use are made from metals, and we use it in a different way also for the manufacturing of ceramics, which is like tough. And looking for use cases with industrial partners to just show the improvement of the manufactured parts that are feasible now. Then thank you for your attention, and looking forward to the questions.